Hello future engineers, welcome to my YouTube channel. If you're still new to my channel, please help me promote my channel by sharing my videos to your friends, friends, because I'm also doing my part to upload lecture videos and sample problem videos that are very important in your studies. This work is very tiring on my part. So to keep me refreshed and inspired, please do so by sharing my videos. That's the only way you can help me promote my channel. So this video will discuss uh, writing shear and moment equations and the constructions of the corresponding shear force and bending moment diagrams by the derived expressions for shear and moment. Except for example 4.8 where we have to derive the shear and moment sections. So for this beam, we have an interhinge here. So derive expressions for shear and moment and draw the shear force and bending moment diagrams for the beam shown below. Neglect the weight of the beam. So first, portion BD is determinate, or we can analyze the reactions for portion BD, BCD. So this is the free body diagram. The horizontal reaction at the hinge is 0. Of course, there's no inclined load. So to solve for vis-a-vis, we sum up moment about D equals 0. So vis-a-vis times 4 minus 30 times 1 equals 0. So vis-a-vis equals 7.5, 30 over 4. Likewise, RD, if this is 7.5, so RD is 30 minus 7.5, so 22.5. There's no need to show it. It's obvious in the figure. Then we draw the left portion of the free body diagram of this beam, AB. Then let's transmit vis-a-vis, which is 7.5 upward here by action-reaction principle. It is downward here. So AY can now be computed. Summation versus Y. AY equals 12 times 6 plus 7.5. So AY is equal to 79.5 kilonewtons. Then let's assume MA is positive. So it is clockwise, positive. Summation moment A equals 0. So MA plus 12 times 6 times 3 plus 7.5 times 6 equals 0. So MA is negative 261 kilonewton meter. So we are now ready to write equations. There are 3 sections here. I will just consider the left as the left segment. I always consider the left portion of the section in writing shear and moment equations. Then you verify this by considering the right section if you want. So this is 79.5 and MA negative 261 clockwise. So at section AB, that's X. So apply the shear AB. That's the positive direction, counterclockwise for moment AB. So remember the shortcut, shear AB is equal to upward minus downward. So 79.5 minus 12x, that's the shear in AB. Then for moment, clockwise moment minus counterclockwise moment. Moment AB is 79.5 times x minus 12 times x over 2. So 79.5x minus 6x squared. Then minus 261 because we have plus moment of negative 261. So that's the moment at section AB, the equation. Then we remove this. Let's proceed to BC. Distance from the y-axis or from A is x. And positive shear, positive moment at BC. So shear BC is 79.5 minus 12 times 6. So that's the equation. Then simplify. 79.5 minus 12 times 6. Shear in BC is equal to 7.5. So it is constant. While moment BC is 79, clockwise movement, 79.5 times x, then plus negative 261, then minus 12 times 6, then the distance of the centroid of this load from this section is x minus 3. So moment BC is 79.5 times x minus 12 times 6 times quantity x minus 3 plus negative 261 or minus 261. Simplifying, 79.5 minus 12 times 6 times x, that is equal to 7.5x, then minus 45. So negative 12 times 6 times negative 3, that's positive, minus 261 is negative 45. So that's the moment equation for section BC. Then we then proceed to CD. As I said, you may consider the right section, which is simpler, but you have to verify that these equations are also the same. Finally, at this section CD, so that's x. Then for shear, previous 7.5, and we have a downward force of 30, so 7.5 minus 30 for shear CD. So shear CD is equal to negative 22.5. It is also constant. And for moment, previous minus the moment of this 30 kilonewton load, this distance is x minus 9. 6 plus 3 is 9. So moment CD is previous moment 7.5x minus 45, then minus the new moment of this 30 kilonewton load, 30 times x minus 9. Simplifying, 7.5 minus 30x is negative 22.5x, then negative 45 plus negative 30 times negative 9 or plus 30 plus 270 is 225. So that's the equation in section CD. So we are now ready to sketch the shear and moment, shear force diagram and the bending moment diagram. First, for shear AB, when x is 0, then it is 79.5 as shown. Then when x is 6, 79.5 minus 12 times 6, the value is 7.5. Because this is a straight line with negative slope, all you have to do is connect these 2 points with a straight line. So that's the shear diagram for portion AB. Then for BC, when x is 6, it is still 7.5. When x is 9, just to the left, it is also 7.5. So it means it is just constant or horizontal curve. Then for CD, when x is 9, it is negative 22.5. Then when x is 10, it is still negative 22.5. So it is just horizontal like that. So since the reaction here is 22.5, so that means if we have an extension here, it will be close to 0. Then for moment, bending moment diagram, for moment AB, when x is 0, it is negative 261. It starts with negative 261. Then when x is 6, because this is an interior hinge, substitute here, it should give us 0 because the moment about the hinge is 0. So it is 0. Now based on slope, the slope initially here is 79.5 and positive, and it is still positive here, which is 7.5, but gentle slope. So to connect these 2 points with a curve tangent to this uh, tangent lines, so it must be concave downward. But based on the second degree curve and concavity, the first derivative is 79.5 minus 12x. The second derivative is negative 12. That's why the curve must be concave downward as shown in the figure. So I hope that you mastered this already. Then between BC, it's not a problem because they are just straight lines. Moment BC is equal to this. This is a straight line. When x is 6, it is 0. And when x is 9 at C, 7.5 times 9 minus 45, it should give us 22.5. So that's 22.5. Then connect with the straight line like that. Then when x for CD, when x is 9, it should give, this value should give us 22.5 also. Then when x is 10 at D, negative 22.5 times 10 plus 225, it should be 0. So again, this is a straight line with negative slope, so you just connect them with a straight line as shown. So that's it. And if we are obliged to draw the elastic curve first, the tangent here is horizontal. This is the curve for this portion. It is concave down, elastic curve. Then in this portion, concave up. So it should look like that. Elastic curve. Concave down, then concave up, passing through the support. So that's it for this problem. So let's have problem 7. Derive the shear force and the bending moment as functions of the angle theta for the arc shown. So let's section this portion AB, and that sectioning should be through point O because this is a semicircular arc. So by symmetry of the loading, this is half of P, this is also half of P. Then let's consider, of course, Cx is 0. Let's consider this portion here. So this is the angle theta, and we have the normal and shear force here. Normal is perpendicular to the radial line, and the shear force is along the radial line. So it should be down through point O. So if this is, and this is the moment, of course, which should be opposite to the moment of P over 2. So I draw a horizontal line through this section. So if this is theta, this angle here is also theta. That's it. Then this is 90 degrees minus theta. So the angle that N makes with the vertical is also theta. So the measure of this angle is also theta. Because this is 90 degrees minus theta. Remember, normal and shear are perpendicular to each other. So this is 90 degrees minus theta. So therefore, this must be theta. So for summation forces x equals 0, so we have V cosine theta, which is where V is the shear in portion AB, minus N sine of theta equals 0. So V cosine theta minus N sine theta equals 0. So the normal force is V cosine theta over sine theta, or V cotangent theta. That's the expression for normal force. For the shear force, summation forces y equals 0, then we have P over 2 minus V sine theta minus N cosine theta equals 0. So transpose this to the right. So V sine theta equals P over 2 minus the value of N is V cotangent theta times cosine theta. So simplifying, V sine theta equals plus V cosine square theta, because cotangent is cosine over sine. So cosine times cosine is cosine square theta over sine theta equals P over 2. So transpose this to the left. So multiply everything by sine theta. So we have v times sine squared theta plus v times cosine squared theta equals p over 2 times sine of theta. Noting that this is just equal to v, because if we factor out v, we have sine squared theta plus cosine squared theta, which is 1. So therefore, the shear equation, which is shear in AB, is p over 2 sine of theta. So that's the answer to the shear in this segment here. For the moment, let's drop this vertical line, and this distance is r cosine theta from O. Then this horizontal distance is radius minus r cosine theta. So that if we sum up moment about this section here, then moment counterclockwise equals clockwise p over 2 times quantity r minus r cosine theta. So moment equals p over 2 times quantity r minus r cosine theta, factor out r. So we have expression for moment AB equals pr over 2 quantity 1 minus cosine of theta. So that's the shear and moment equation for this section here. Then for the section BC, so if this is theta, from this axis here, so going that way, if this is theta, then this is 180 degrees minus theta. Or if I call 180 degrees minus theta as alpha, so this is 90 degrees minus alpha, 90 degrees minus alpha, so this must be alpha. So what is alpha? 180 degrees minus theta. So 180 degrees minus theta. So x sub 1 is equal to r, this is radius r, and this portion here is r cosine of 180 degrees minus theta. So therefore, x1 is r minus r quantity cosine of r minus r cosine of quantity 180 degrees minus theta. So if we expand cosine of 180 degrees minus theta, then it is equal to cosine 180 cosine theta plus sine 180 sine theta. Sine 180 sine theta is 0. So cosine of 180 cosine theta is negative cosine of theta. So this portion is negative cosine of theta. So x sub 1 therefore is r minus r times negative cosine theta, or r times quantity 1 plus cosine theta. So having found x sub 1, we can now set up summation of moment at 1 to solve for M1, or moment in BC. So M1 is equal to P over 2 times X1, or P over 2 times R quantity 1 plus cosine theta, or M1 minus P over 2 times R quantity 1 plus cosine theta equals 0. So M1 or MBC is PR over 2 quantity 1 plus cosine of theta. So that's the moment equation for portion BC. Then for shear 1, we need to solve N1 first. So we sum up moment about O to have our analysis different from the first segment. So summation moment about O equals 0, so we can derive the value of N1. So N1 times R plus M1. So summation moment at O about O equals 0. So N1 times R plus M1, which is PR over 2 1 plus cosine theta, equals P over 2 times R. So we can cancel out R. So in the right side, we have P over 2 left. In the left side, we have N1 plus P over 2 times 1, which is equal to P over 2. So we can cancel P over 2. So N1 plus P over 2 cosine theta equals 0. So therefore, N1 is negative P over 2 cosine of theta. Then summation of moment, or summation of forces along x equals 0. Then we have shear 1 cosine of 180 degrees minus theta plus n1 sine of quantity 180 degrees minus theta equals 0. So remember that from trigonometry, sine of an angle is equal to sine of its supplement. So simplifying sine 180 degrees minus theta, it is just sine theta. And cosine of 180 degrees minus theta is negative cosine of theta. So we have v1 times negative cosine of theta plus n1 times sine of theta equals 0. Substituting the value of n1, so we have v1 times negative cosine theta plus negative p over 2 times cosine theta times sine of theta equals 0. Canceling out or dividing everything by negative cosine theta, so this becomes v1, this becomes p over 2 sine theta equals 0 after we divide everything by negative cosine theta. So again, v1 plus p over 2 sine theta equals 0, or shear 1, which is shear BC, equals negative p over 2 sine theta. So that's the shear equation for portion BC. So I hope that you're able to follow the solution, especially the trigonometric simplifications of these equations here. So that's it for this problem.